This is question 11 from the third CSAT sample paper. In this question we're given an integral in in terms of n, and that's the integral of cos to the nx dx between minus pi by 2 and pi by 2, where n is any non-negative number, so greater than or equal to 0. And we're asked to find a recursive expression for in first. So if you want to have a go at this part yourself, pause the video now. Okay, so how are we going to approach this? Well, you've probably seen at A-level that often you get recursive expressions for this kind of thing by splitting this up into two things multiplied together. And that makes sense. We have to split this up somehow. We can't really use identities because we don't know what n is. We don't really want to make a sum of things because it will probably get complicated, so it makes sense to make a product of things. And if we have a product of things, then we can use integration by parts. So at least there's some way forwards once we do that. So how do I want to split this up? Well, you might consider splitting it into cos squared and cos to the n minus 2. I think that can eventually work. It's probably easier first to go for cos times cos to the n minus 1. So just split off one lot of cos. And then we're looking for a way to decrease the power of n. Well, we've done it already by taking out a factor of cos. Unfortunately, we have to do more steps to integrate this. So we're likely to do this by parts. We've got two things multiplied together. If we do that, we don't really want to be integrating this because it depends on n, which could be arbitrarily large. So that would make it quite complicated. And it's quite easy to integrate this, whereas differentiating this isn't so difficult. And differentiating this will decrease the power of n again, which is fine because as long as we have in depending on some earlier value of n, it's still recursive. So what we don't want to do is, if we integrate it, we'd probably have just n's up here, which can be okay, it might not. It's safer to decrease the power. So we're integrating this and differentiating this. So if we do parts, first we have this integrated times this left alone, and cos when we integrate goes to sine, and that's between the same limits of minus pi by 2 and pi by 2. And what does this actually equal? Well, it does depend a bit on the value of n. So at pi by 2 and minus pi by 2, cos is 0. So as long as we have n greater than 1, this will be 0. If n is equal to 1, then this will actually be 1, and this whole bracket will come to 2. If n was equal to 0, we couldn't do this step in the first place, or it would be a very bad idea. We couldn't integrate like this, or like we're about to do. So 0 and 1 are special cases, but that's fine because when you have a recursive expression, normally the first value or the first couple of values are just given, and then the recursive expression gives you all the later values. So this will only work for n greater than 1, but that won't be a problem. What's the second bit when we do this by parts? Well, we take away the integral of this differentiated, so it's still sine x. Sorry, this integrated, so it's still sine x. And then this differentiated, so what happens when we differentiate? Well, we bring down the n minus 1 and then decrease the power. But we also have to use the chain rule, so we have to multiply by the derivative of cos, which is minus sine. So we get a minus in here and we multiply by sine. And what does that mean this simplifies to? Well, we can ignore this now because we're setting equal to 0 for n greater than 1. And we can take out the n minus 1 in front of this integral. The minuses cancel. And then we've got two factors of sine. It gives us sine squared and one factor of cos to the n minus 2. So what we want is something involving k for k less than n to make a recursive expression for this. And we've got these signs in here which stop it looking like this integral. So we need to get rid of the signs, but that's fine because we have sine squared, so we can use sine squared as 1 minus cos squared. If we do that, we get inside the integral cos to the n minus 2 times 1, and then times cos squared gives us minus cos to the n. And then we can break up this integral into two parts. The first one's going to be in minus 2, and the second one's going to be in. So we get n minus 1 times in minus 2 minus in. Remember, there's an in over on the left here, so I can bring this over to the left. I'm adding n minus 1 lots of in, so I get n lots of in on the left. And on the right I still have n minus 1 lots of in minus 2, and then I can just divide both sides by n to get in terms of in minus 2. And you might be more used to seeing in defined in terms of in minus 1 in recursive expressions, but defining it in terms of in minus 2 is still just as good, it's still recursive. The only issue we might have if we were trying to find in now is we'd have separate cases for odd and even values of n. So if n's an even value, then it's only going to depend on previous even values of the integral, and if it was odd, it would only depend on previous odd values. So actually we get two, if you worked them both out, we get two very different sequences. As it turns out, they're only going to ask us to do this for n even, so we don't have to worry about what happens when n is odd. It's also just worth recapitulating this. This only works for n greater than 1, so n equals 0 and n equals 1 are special cases. Okay, in part 2 we're asked to find a non-recursive expression for I to n using 2n choose n. And they actually say the simplest, so you're meant to simplify it as far as possible. And we'll use this which we found in the previous part. So if you want to have a go at this part yourself, pause the video now. Well, one thing I'll note at the beginning is, remember this worked for n equal to 2 or bigger. So we can have I0 here, but we can't have it on the left because then this would be I minus 2, and that's not defined and it's meant to be non-negative. So we have to kind of start with I0 and work out what that is, and then we can use this recursive relationship to find out the other even values of n. Basically, that's what this means. We're looking for this to be even. So what is I0? Well, we just take the expression for in, which is the integral of cos to the n between these limits, and stick in n equals 0, but cos to the 0 is 1. So it's just the integral of 1 over this range, and that means it's basically just going to be the length of the interval from minus pi by 2 to pi by 2, which is pi. So the value of this is pi. Let's think about, well, we could start with I2 and then look at I4, etc. I think that's just going to waste time. It's easier to look at the general case first. So if I start writing, I'm going to put 2k here for n. I know they use 2n here, but I think it's confusing if we change variables, since the name of the variable doesn't matter. So I use 2k here to make sure this is an even number, and then replacing n with 2k everywhere, we get 2k minus 1 over 2k times I 2k minus 2. And what's going to happen, I want to repeat this process so that I can eventually get down to I naught. So I could replace this term here with 2k minus 3 over 2k minus 2 times I 2k minus 4. And I'd get this term in there, and I can just keep repeating all the way down until I get to where k is equal to 1, and then I have 1 over 2, or half, times I naught. So now we just have to try to simplify this, and remember we're looking to have this binomial coefficient, 2n choose to n, or in this case 2k choose k. So I need to get some factorials in that case, which because the binomial coefficients are defined in terms of factorials. And that's okay because we've got products of numbers, but if we want a factorial, we're looking for the product of all the numbers up to some number. Whereas if you say look at the top, we've got basically all the odd numbers up to 2k minus 1, and on the bottom all the even numbers up to 2k. So there are some numbers missing. So here we're going to have to use a trick that once you've seen once, it's just a little bit of work to reapply it, but it's a little bit of working to do to show how it works the first time. So I've just put that working here, but we'll zoom in to look at it. So suppose first of all we look at the even numbers, basically everything up to 2k, so 2k times 2k minus 2 all the way down to 2. What is that? Well, we can split it up as 2 times k times 2 times k minus 1 times another lot of pairs of 2 times a number all the way down to 2 times 1. And that's good because we've got a 2 in each of those terms, and then the remaining bit is k, k minus 1, k minus 2, etc. all the way down to 1. So that means we have k lots of 2 is 2 to the k, because there are k terms, and then the other terms are k, k minus 1, etc. And now those are just a factorial, they're k factorial. So that means the product of all the even numbers up to 2k is 2 to the k times k factorial. So okay, that will help us with the bottom of our expression here. But we need to deal with the top, which is the even numbers, so you have to figure out how to deal with them. You obviously can't take out a factor of 2 each time, like we did for the even numbers, so what can we do? Well, here the thing to notice is, if we have all the odd numbers up to here, that's the same as all the numbers up to 2k divided by just the even ones. And since we know all the numbers up to 2k multiplied together is 2k factorial, and all the numbers up to 2k, or the even numbers up to 2k, we have an expression for now. It's 2 to the k times k factorial. That means that we can use those to find an expression for the product of the even numbers, sorry, the odd numbers. So let's look at that working quickly. If we have all the odd numbers up to 2k minus 1, that's the same as we had all the numbers up to 2k divided by all the even numbers up to 2k. And so you could do this up to 2k minus 1 and have the even numbers up to 2k minus 2 instead. The reason I'm going up to 2k is it makes the working a bit simpler because there's going to be k terms on the bottom, and also we know we're looking for a binomial coefficient with 2k in, so it makes sense to look for 2k factorial. So on the top we have the numbers up to 2k is 2k factorial, and on the bottom, the same thing we just worked out, 2 to the k times k factorial. So with that in mind, we can simplify this expression. We've got 2 to the k, let me zoom in, we have 2 to the k factorial over 2 to the k factorial on the top, but on the bottom we've got another lot of 2 to the k factorial. So if I multiply, I'm going to multiply by this on the bottom, so it gives me 2 to the 2k and k factorial squared. And then remember that I naught we worked out to be pi up here, so I naught is pi. And that means this is our expression for I2k. The only thing we have to do is we're meant to get that binomial coefficient. So remember that if I have a choose b, that's a factorial divided by b factorial times a minus b factorial. I will note here that factorials are defined for k equals 0, and it's just equal to 0 factorial is equal to 1. So we have if we substituted in k equals 0, we'd actually get 1 on the top and the bottom, and we just get pi, which is correct. So this does also work for k is 0. And if I rearrange to try to get all the factorials together, I can write it as 2k factorial on the top, and then k factorial times 2k minus k factorial, because 2k minus k is k. And now this looks like a binomial coefficient, because I've got a factorial over b factorial times a minus b factorial. And then the other stuff I've just taken out on the left here. So this part now just becomes 2k choose k, which is what we were asked to include. We're not going to be able to put this into a binomial coefficient, at least not easily, and not simply. So we'll leave that on the outside. One thing to note here is they asked for the simplest form. I'm not sure whether they would consider this simpler, or if we made this into 4 to the k, whether that would count as simpler. They should probably accept both, because I don't see that one is significantly simpler than the other. But otherwise, this is your value for I2k as asked.